Let's take a little aside, an important aside, to again motivate why this might actually make sense to unify these cases. Let's look at the physics. So here's an applet from Geneseo University, which is that they use D instead of C, but they've got the standard equation here. They have initial condition 5, which shows up best on their screen. And I put in a damping constant of 3. And it turns out that that's very highly damped. So solve. It's off the screen, I know, but I just solved it. And now I'm going to animate. And so you can see the spring just kind of peters out. Not a lot of oscillation. Okay, and we'll see how to solve this explicitly. But it's plausible that if there's a lot of friction or other kinds of damping, then it's just going to go and not really oscillate. Okay, now I'm going to turn down the damping progressively. Let's turn it down to about 2.1. Okay, take a careful look. It's not going to look drastically different. Still going to kind of just peter out. Okay, but now I'm going to take it down to 1.9. Let's see. Well, we may or may not be able to see something interesting there. Oh, you can just barely see it. Now look what happens. It seems to do almost the same thing, but notice just a tiny little bit of up and down on that graph there. There is some oscillation. It's a highly damped oscillation, but there's some oscillation. Okay, let's take it down to 1.5. Less and less damping. The system gets to keep more of its energy longer. Oh, okay. It's still pretty small, but you can definitely see some oscillation there. If we take it down to 1, okay, now you can even see it on the left-hand side just a little bit. And if we take it down to 0.5, not 0.5, 0.5, we're going to see, quite significant. It's definitely a damped oscillation. Okay, and notice what we're getting. This is the kind of thing you'd get from a mixture of damping, an exponential decay, and a cosine or sine. Okay, in fact, we're going to find out it's just a product of the two. And so we're getting this progressive motion, and let's look at 0. That's going to look familiar. This is the one case we know how to solve, where there's no damping at all and we get a pure cosine wave. Okay, so there's complementary things to talk about here. One is how different qualitatively the end curves looked like. This compared with the highly damped curve situation, these don't look very much like each other. That would suggest a difficulty in unifying the cases. But look at what happens let's look again, 2.1. Okay, so now I want to emphasize not the difference in these curves between this and oscillation, is the similarity. This thing damps down, it's flat, okay? And now at 1.9, yes, there is a qualitative difference in that it oscillates and you have an infinite number of local max and minima. But in terms of, did the graph move very far? I just did it. Did you notice? Did it change a little bit? Not very much, okay? And so that again says there should be unifying theory here, where we can see that tuning, in particular tuning this parameter, which we'll look at in detail in a little bit, should give us some smooth change between a family of solutions. And unless we unify these cases, we're never going to be able to really understand that. If we say on one hand it's exponentials and on one hand it's cosines and sines, we're not going to understand that very well. And introducing this new kind of algebra, introducing complex numbers, lets us unify this in a very beautiful way. So here's the motto here. This is the Wikipedia model, if you've ever edited on Wikipedia. Be bold. Let's invent some new algebra. But with a lot of provisos. It's not just blindly inventing stuff just for fun. It's got to be self-consistent. It's got to solve quadratics, hopefully all quadratics, or at least ones with positive coefficients to solve our fundamental problem. When we've got to be able to use those solutions, let's call them alpha, no, not for any incredibly important reason, in exponentials. That was the whole point, that was our guess for the y of t that might solve those guys. It should, I guess I didn't put it on here, but it should seamlessly make sense when alpha is an ordinary number or one of these new kinds of numbers. And as we change alpha gradually, it shouldn't do anything particularly weird. Okay, it of course should solve the core problem. It should really work as advertised, that when I put in one of these guys, it honestly does solve the core problem. And in particular, it should reproduce the cosines and sines, the oscillation of the physics and the known solution to, say, this core problem, like, minus 4y. And of course, it should have something to do with the geometry of circles. And that's going to be one of the prettiest parts of the whole story. Okay, so Um, let me just end that there. Make this a short video, and then we'll jump into. This is really the start of the PDF part two. And so now's a good time for you to go and look at that and do as much as you can on your own.